I'm Dong from University of Rochester, and today I'm going to present the work done with my collaborators, Fang Zhou, Chen, and Shui, on locality analysis through static parallel sampling. So locality analysis is the measurement of distances for the reuses, and it is important as there is a mismatch for the latencies of memory accesses and arithmetic operations. On modern CPUs, memory access latency could be 50 times larger, and things are worse on GPU cores. So to bridge this gap, a number of locality-centric optimizations are often performed by programmers, compilers, or runtime systems, such as tiling, generating catch hint, or program grouping, or catch partition. And to get this kind of optimizations, locality measurement are needed. So there are mainly two ways. One is trace-based analysis, which first run the program to collect its memory access trace. Then we scan the trace to detect the reuses, such as reuse at address A1 and reuse at address A0. And during the scanning, the distances for the reuses are often counted. They are counted for either reuse distance, which is the number of the distinct memory access between the use and its reuse, or the reuse time, which is the number of memory access between the use and its reuse. So here, A1 is accessed twice between the use of A0 and the reuse of A0. So the reuse time of A0 is one larger than its reuse distance. So once we get this distance, locality metrics are performed to derive the catch performance. So the other method is static analysis, which collects the static information, such as the subscript expressions for the indexes, for the references, or the induction variables, the lower upper bounds for the loops. With this information, mathematical formulations for reuses are often built, either to derive the catch line usage, or the catch misses, or the reuse distance. And to solve these equations, integer linear programming may be needed. So trace-based analysis requires to run the program, and static analysis currently is restricted to the linear, restricted to the fine expressions. So our approach, static sampling, utilize the code structure from the target program to generate the minimum program flow to find the reuse and its distance, which removes the need of the reuse formulation and solving. So the affine restrictions is no longer there. Our system is like this. We take the LRV and IR of the target code, then we extract the code structure information, such as the loops and the memory references. And from this tree representation, we generate a sampler, generate a specialized sampler code. And by running this sampler code, we can get a distance histogram and derive the Mies ratio curves. So I will introduce, first introduce the baseline framework, then introduce its specializations. So our baseline framework is like this. The generated code is shown on the right, and the target program is shown on the left. So for the generate code, we for each static references in the target program, we generate one sampler function to sample the reuses starting from it, such as A0 sampler is generated to sample the reuses starting from Aij. And sampler B and the B0 sampler is generated to sample the reuses starting at Bij. And inside each sampler function, we first generate one loop and several assignment statements to control the number of samples to take and choose which iteration to sample. And combine this sampled iteration with this sampled reference, we actually sampled one access. And starting from the sampled access, we reconstruct the program flow that following it. Here, the nested ij loops are regenerated. And we also use a counter to count the number of memory accesses that happens after the sample access. And in addition, for the memory references accessed to the same reference as the sample does, we also generate one address checking if statement to see whether they have access to the same location. So if the address matches, we accumulate the counter result to the histogram and break to next sample. If it does not match, we continue to follow the program flow. And by running this sampler code, we can get a sampled distribution for the reuses. And this sampler does not have any real memory accesses in the target program. And also, all the calculations that are not related to the address calculation are also removed. So one thing we may need to pay attention is the number of samples here. So as different static references may generate a different number of dynamic memory accesses. So the number of samples we take for each static reference should be proportional to its actual access number in order to make sure all the reuse times are sampled with equal probability. So with the correctness ensured, the precision of static sampling under the selected number of samples is determined by the way we choose samples from the iteration space. So we compare fixed stress sampling with random sampling using a 5-point stencil program as a case study. So we first measure the reuse time distribution by tracing. And you can see that there are 6 different reuse time, and each of the first 4 occupies almost one quarter of the total number of reuses. And the last 2 occupies 0.02% only. And then we run stack sampling with fixed stride and random sampling with sampling rate 0.01% to 1%. So from the result, we can see that all the static sampling results are good approximations for this one. And for the same sampling method, more samples will lead to more precise result. And for the same sampling rate, random sampling can perform better, so they can get get more precise distributions. You may notice that even when we increase the number of samples for fixed stress sampling, they still miss the last reuse time, because this reuse time can only be generated by the iterations from the last column of this 2-dimensional iteration space. So even if we shorten the stride, as long as the number of samples does not fall into the last column, we can not get it. So by default, we use random sampling. So with the understanding of the baseline framework, I will introduce several specializations. So in the baseline framework, we reconstruct the program flow and search for its reuses. This process can be accelerated when we have more static information, such as dependence distance vector. Dependence distance vector is the number of iteration difference between the dependent source and sink. The shortest one indicates the reuses. So for the reference with dependence distance vector available, we can remove the searching process. If the dependence distance are available for all the references, the entire searching process can be removed. We have a catch-line granularity reuse iteration derivation algorithm in the LSPC post paper. And even if we don't have more static information, there's still a chance to avoid iterating. So as reuses from the same reference may generate the same distance, or the distances are following some patterns. So we can first perform searching for first several samples, then predict its memory access pattern. With the memory access pattern predicted, for the following samples, we can directly predict its reuse iteration and predict its distance. And we also have one additional checking to check whether the predicted iteration have accessed the same location. And if they have accessed the same location, we accumulate to the counter and the break. And if they have not, we will do the searching process and adjust the memory access pattern. And in our implementation, we just use a simple linear regression algorithm to do this. And as you may notice that the length of the reconstructed flow is determined by the number of memory references that are related to reuse searching, and all the memory references are converted to counter increment statements or the rest checking if statements. If we can remove the counter increment statements, we can make the flow shorter. So we have a symbolic algorithm to derive an expression to calculate the reuse time by giving the starting iteration and the reuse iteration. So it's like this. So we have the 5-point stencil program. We have the tree representation, and also the top two are the two nested loops, and the round one are the memory references. We assign a local order for all the memory references, and for use at A1 and reuse at A3, we can generate the expression like this. And the iteration for this expression is that we first assume use and reuse are happening at the use position. So A1 here. So the first two terms are calculating the iteration, the number of memory accesses in between, and then we calculate the difference here is 3 minus 1. We have an algorithm that can calculate this expression for arbitrary tree structure, which means arbitrary loop structure. I will not go through it here because of the timing limitation. So besides performance concern the specializations, we can also adjust the target of the analysis. For example, if we want to know the catching effect for different subset of arrays, we can choose to generate a different set of counter increment statements. So, for example, if we want to know the catching effect for A, we only need to generate the right counters, and if we want to know the catching effect for A and B, we generate the right and the blue counters. And in this way, we can know the catch performance for different subset of arrays. And in addition, by comparing this result, we can know how different arrays reuses are interfere with each other. So here the reuse time 3, 4, 5 shifted to 4, 5, 6 by adding a repeat to the caching set, and 5,000 to 6,000. So at last, this framework is easy parallelizable, and as there is no dependence between different samplers and no dependence between different samples inside the sampler, so we can choose the granularity to parallelize it according to the need. So our implementation is based on LLVM. We have several LLVM analysis paths to extract the static information and build as a tree representation, and a code generator to generate the static sampling code. And all the evaluations are performed on linear algebra and the stencil benchmarks in the polybench and one FST bit reversal loop. And precisions and overhead are compiled with tracing for RU fully associative catch with 64-byte catch lines. And all tests are performed with the RVM 4.0 and macOS. So the precision is like this. We first measured the full trace means ratio curve, and it's marked by the solid red lines. And then we scale the sampling rate from 0.01% to 5% per loop. As you can see from for the lowest sampling rate that can generate a means ratio curve, it's triangular marked lines and these orange lines. These lines are only one samples per loop, and it can almost catch the shape of the means ratio curve. And the more samples we have, less errors we got. And for 2% sampling rate for all the benchmark we have tested, they get almost overlapping means ratio curves. And for overhead, there are two overhead. One is the time to generate a static sampling code from our tool, and we can see the maximum generation time is 0.02 seconds. And this overhead increases when the code structures are becoming complex, such as they contain small reuse searching related references, such as the convolution 3D and convolution 2D, or they contain small reuse searching related loop structures, such as 3MM. And the other overhead is the time to run this generated sampler to get the means ratio curve. On average, we can see it's 0.05 second, which is 32 times faster than tracing. And the parallelization is done by reference granularity, and we perform this by just by wrapping the sampler function with C++ thread creating functions, and running on for 224 codes, we can get the speed up 1.68 to 2.55. And this speed up may be limited because reuses are not distributed evenly for different references. So most of sophisticated parallelizing approach can be left for future work. So our tool is available on GitHub, and I'm ready to take questions.
Thanks. These are impressive results. And in the end, so I had, let's say, mostly one question. So I was not sure about the code generation method that you are considering. I mean, what kind of hypothesis you make on the control flow or AST? So you're using static control benchmarks except for one. So what kind of hypothesis do you make on the program?
For currently, the hypothesis should be as we take algorithm IR for of the code. So as long as we can detect the high-level structures from the LVM IR, we can do that. We can perform this technique.
So can you have like while loops as well? Or?
While loops, I haven't tried it yet, but if the while loop can be converted to for loops, then probably this technique can handle it.
Sort of along the same lines, what happens if the data access pattern is determined at least partly by the contents of the data?
It's basically the indirect memory access, right? For this technique, you can adopt it in two ways. So one is that you just analyze the regular, the direct memory access part, and left the rest of the work to the dynamic tracing. And the other is that for this static approach, we don't take any input of the program. So here we don't take any input of the program. We can still generate this flow, but we take the input. And when we want to make some control flow decisions, we can use that in the data.
If there are no more questions and there is more time, I have one more. Maybe it's a naive question, but you didn't seem to make hypothesis about the associativity. So in the experiments, you assume it's fully associative.
Oh, okay, yeah.
But the sampling may interact strangely with this. So can you say that?
Yes, yes. Actually, the beauty of this footprint metric, locality metric, is actually decoupled the process. It's a machine independent metric. As long as we get the distances, we can derive the catch performance for associative catch, but I didn't include it in this paper.
But that was the previous,
yeah,
that was the ASPAS paper.
In that paper, yeah.
Any other questions? Okay, let's thank Dong again.
Thank you.
And let's thank all of our speakers again for a fantastic session.